Imagine the global internet as a shipping lane. Every single second, massive fleets of data are pushing through the water, carrying the millions of requests, messages, and transactions that keep our apps running. But the containers holding all that data, usually standard formats like JSON or XML, are inherently inefficient. If you look inside a JSON payload, you won't just see the actual information, like a user's name or their favorite number. You will see the descriptive labels, like username or favorite number, spelled out in text over and over again for every single record in the database. When you scale that up to millions of records, you are suddenly transmitting gigabytes of the exact same words. It's like shipping a tiny memory card inside a massive wooden crate. The payload becomes mostly heavy, useless packaging. These self-describing formats are easy for humans to read, but that readability is a trade-off. At scale, it forces servers to push massive volumes of redundant metadata across the wire. To fix this, we can look at how a fast food drive-thru works. Instead of saying, "I want a burger with 2 patties, cheese, lettuce, and special sauce," you just say, "I'll have a number 1. You and the cashier share a menu, so a single digit perfectly communicates a complex order. Tools like Apache Thrift and protocol buffers do the exact same thing for data. They rely on a shared schema, which assigns a unique number, called a field tag, to every single piece of information. Once the sender and receiver both have a copy of that schema, we can step into the payload and simply delete the long text strings describing the data. Wherever those bulky words used to be, the system drops in a single-digit integer. Because the computers agreed on the strict schema beforehand, they can instantly decode those numbers. They transmit pure meaning without sending a single word of text. Text isn't the only thing weighing down the network. Once the words are gone, the next major bottleneck is actually the invisible, empty space hiding inside the numbers themselves. This diagram shows how computers traditionally store numbers. To be safe, a system often reserves a rigid 8-byte block of memory for an integer. But if you are only storing a small number, like the number 5, you only use the very first slot. The remaining 7 slots are totally empty, like a giant suitcase packed with a single pair of socks. Protocol buffers and Thrift's compact protocol fix this by using variable length integers. Instead of a fixed size, the digital container dynamically resizes to fit the exact dimensions of the data inside it. All those wasted slots collapse into a tightly packed 1-byte container. Engineers took it further. Both the data type and field tag number slide together into that exact same byte. Applying this physical optimization everywhere crushes an 81-byte JSON payload to barely 33 bytes. To make networks truly efficient, developers had to squeeze the invisible empty space completely out of the architecture. But making the data smaller creates a new risk. Tech companies are constantly updating their code. Trying to update the schema on millions of distributed servers all at the exact same moment is impossible. If an old server gets a new, shrunken payload it doesn't recognize, it will crash. To prevent those crashes, developers followed 2 strict rules for schema evolution. First, once a field tag number is deployed into the wild, it can never be changed or reused. Second, if you add a new field tag to the menu, you must make it optional or give it a default value. These rules create forward compatibility. An older server safely receives a freshly updated payload containing brand new tags it has never seen before. When that old code hits a new tag, it looks at the data type annotation stamped right on the block. It calculates its exact physical width and simply jumps completely over it to read the next block it recognizes. The strict physical architecture of the field tags guarantees that servers won't panic when they encounter the unknown, keeping the system stable during software updates. Packing, unpacking, and routing this microscopic data while gracefully ignoring unknown variables requires incredibly complex parsing logic. So, who is actually typing all that code out? Usually, nobody. These formats rely on a tool called code generation to automate the heavy lifting. Developers write out the simple, human-readable schema rules exactly one time. The code generation tool will then automatically translate it into the highly optimized source code for Java, Python, C++, or whatever language the system needs. By automating the translation and stripping out the text, Thrift and protocol buffers solved the dual threats of massive bandwidth bloat and dangerous software updates. But those field tags still take up a tiny amount of space in the payload. To shrink the data any further, you would have to figure out a way to eliminate the tag numbers entirely. Field tags made data serialization fast and reliable, but to reach the absolute limit of efficiency, the next evolution, Apache Avro, would find a way to eliminate those tag numbers altogether.